Welcome students into the series of lecture on statistics. And in this series of lectures on statistics, we are in continuous probability distribution. In continuous probability distribution, we completed normal distribution, we completed t-distribution. In the last session, we discussed about the chi-square distribution, and this is a continuation video on chi-square distribution. Okay, in the last lecture, what we did, we discuss a very important concept that every entity in this world does not follow normal distribution or t-distribution. Entity like stock prices, bond prices does not go to negative. It doesn't have any value less than zero. Therefore, the distribution like normal distribution and t-distribution doesn't work because these distribution gives you the value which are negative, and in the left direction they goes up to negative infinity. So therefore, we need a distribution which is a right-skewed distribution. Now, there are different types of right-skewed distribution, but the distribution that we have chosen for the discussion is chi-square distribution. And we established one of the most important point that not every right-skewed distribution is not chi-square distribution, only if the standard normal data, if there is a standard normal data, and if you do the sum of square of standard normal data, that will approach chi-square distribution. That will approach chi-square distribution. Okay. And today, the focus of the session is to interpret and read the chi-square table. But there is a problem. The problem is you cannot read, you cannot understand, you cannot interpret chi-square table until and unless you have discussed these 3 points in detail. First of all, you should understand what is degree of freedom. Second, you need to understand that how the sum of square of standard normal variable, the sum of square of standard normal variable approaches chi-square distribution, how something which is normally distributed, which can go up to negative value, which can go up to negative infinity, approaches chi-square distribution, which is pegged at zero. So this is the second point that we have to understand. And then we have to understand how chi-square distribution is a family of distribution. Then only you would be able to understand this, which is the chi-square table. Okay. So before understanding the chi-square table, let's take support of a sheet. In that sheet, we did the sum of square of standard normal data, and we'll observe whether it is approaching chi-square distribution or not. Okay. So this is our sheet, and understand what's happening. So what I did, I first generated a random number. Column A is random numbers between 0 and 1. For that, I have used rand function of Excel, and it is giving me a random number from uniform continuous distribution between 0 and 1. Okay, perfect. So how many random numbers I have generated? I have generated near about 200 or 199 random numbers. Perfect. Now these random numbers are from uniform continuous distribution. This is not in the shape of normal distribution, or it is not standard normally distributed. What is standard normally distributed entity? Any entity which is normally distributed with a mean of 0 and standard deviation of 1. Very important. Please be focused. Any entity which has a normal distribution but with a mean of 0 and standard deviation of 1 can only be called as standard normally distributed. Okay. So how we can create a standard normal distribution or standard normal data in Excel with the help of a random number. So for that, I have used norm S inverse function of Excel that will convert the data into normal distribution with a mean of 0 and a standard deviation 1. So what it is doing, it is converting all the data point, see, it is converting all the data point into a standard normal distribution. But please understand, I haven't taken 100,000 data point. I haven't taken 10,000 data point. I have just taken 199 or 200 data points. If you calculate the mean, see, I'm calculating the mean with the help of average function in Excel. If I calculate the mean is near to zero. Mean is near to zero. And standard deviation is near to one. It is approaching the mean of 0, it is approaching standard deviation of 1. So every time, please understand, any data sets try to approach normal distribution, try to approach chi-square distribution. Every time you won't see the real world data which fits exactly the normal distribution. Okay, this is a very important lesson. Similarly, if you change the random number, let's change the random number. If you change the random number, see the mean is now negative. Standard deviation is now 0.95. Let's change it again. If you change it again, see the standard deviation has increased and mean has become positive. On an average, you will see if you keep on taking such random number, or if you increase the sample size from 199 to 100,000, then mean will become 0 and standard deviation will become exactly equal to 1. So please understand the limitation of the data. If the data of the sample size is less, even if you're using a function from Excel which is converting the data into a standard normal variable or standard normally distributed entity, still the mean and standard deviation is not 0 and 1, it is approaching 0 and 1. Perfect. So what is this standard normal? If you remember what is standard normal, anything which is normally distributed with a mean of 0 and a standard deviation of 1. So this column B is standard normal data set. Now what I have to do? I have to square it first and then sum it up. So what I did, I square all the values. See what I did? I square all the values. What I did, I squared all the values. Let me repopulate the numbers. I squared all the values. I squared negative minus 1.014. This is the value. I squared 2.2549. This is the value, so on and so forth. What is the next step? I have to sum these value. How many values? How many z square I have to sum? Is it 1? Is it 2? Is it 3? Is it 4? Is it 5? For the time being, see, for the time being, I'm summing up 5 z square value. 5 sum of square of standard normal data set. 5. Not 6, not 4, not 3. 5. See this number? This number is generated by summing C3 till C7. Again, 5 values. See this? It is generated by summing 1, 2, 3, 4, 5 cells. So actually, how many Z I'm summing up? 5. And that is your degree of freedom. That is your degree of freedom, which is also denoted by K, which is also denoted by K that you see on the screen. That is also denoted by K. Actually, it is what? Degree of freedom. What is degree of freedom in chi-square distribution? The number of standard normal data set you are squaring up and adding. Is it 5? Is it 6? Is it 7? For the timing, it is 5. See what is happening. This is my data set, and I calculated the probability associated to this data. So this is my data, and this is the probability associated to it. This is my data, and these, the column J is my probability. I plotted it. When I plotted it, what happened? I got this distribution. See, this is not perfectly giving you a shape of chi-square distribution, but if you keep on changing the number, and if you keep on changing the number, and if you keep on taking the average of those number or average of those probability, on an average, it will approach chi-square distribution, which is pegged at 0 in the left-hand direction, which is pegged at 0 in the left-hand direction, and going up to infinity, right? Or you can interpret it like this. Currently, the sample size is only 199. If you increase the sample size to 100,000, this distribution would start approaching what? A perfect chi-square distribution shape, a curve, right? So what is the lesson? The lesson is not every time it is going to show you the exact chi-square distribution. The assumption is that this will approach chi-square distribution if the sample size is large enough. Okay. So this was the plotting. This was the plotting for 5 standard normal data. What if I increase it to 10? So what I did, I increased the number to 10. How? Again, this is random number. I'm converting it into standard normal data set. I'm squaring it up, and now I have to add all the squared standard normal data set. But see, how many standard normal data set I'm squaring it? It is only 10. See, it is only 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not 5, it's 10. Again, this is 10. Again, this is 10. And you see, I plotted this against the probability. Against the probability. Column J is again the probability. I plotted it. And when I plotted it, again you see a pegged distribution at 0, then it is getting a peak, and then it is approaching infinity. But again, please understand, the shape of this distribution is different from the shape of this distribution. They're not identical. If you change on the number of standard normal data set you are adding, If it is 5, the shape is different. If it is 6, the shape is different. If it is 7, the shape is different. If it is 10, you have a different shape of chi-square distribution. And that's why chi-square distribution is a family of distribution. What? It is a family of distribution. It is a family of distribution. For k equal to 1, this is the shape. For k equal to 2, this yellow line is the shape. For k equal to 3, this green line is the shape of chi-square distribution. And every row in this chi-square table is representing one specific shape of chi-square distribution. This is critical. And what is this degree of freedom? Degree of freedom is how many z you're adding up, how many standard normal variable you're adding up. Is it 1? Is it 2? Is it 3? Is it 4? Is it 5? We had just looked into what will happen if I add 5 standard normal variable, the square of 5 standard normal variable. And we also looked into if we add 10 standard normal variable, then what would be the shape? But in both of them, what you have to understand that both of them will approach chi-square distribution. If the sample size increases, or if you keep on changing the random number and take the average of all the random numbered plotted probability distribution, that will be on an average chi-square distribution. Now the last point, how to read this chi-square table. How to read this chi-square table. Let's randomly select 13.277. So when I read 13.277, first of all, look for the degree of freedom. The degree of freedom is 4. So actually, you have to look into the shape of the chi-square distribution, which has a degree of freedom of 4. So basically, degree of freedom of 4. So assume this is that chi-square distribution. Now, when you write this 13.277, when you plot this 13.277, you have to look into this number that is 99%. 99% means that when you plot 13.277, then you will cover 90% area towards the left of this number. Similarly, take any other number. Say we have taken 2.833. So what you have to look for? First, you look for what is the degree of freedom. Degree of freedom is 7. So we have to look into the chi-square distribution where the degree of freedom is 7. So there would be a different shape. So there would be a different shape. So assume this is the shape of the chi-square distribution where the degree of freedom is 7. Now, when you plot this 2.833, you have to look into what is the area given. The area is 10%, which means that if you cover the area between or the left hand side of 2.833 till 0, this area would be 10%. And the area in the right hand direction is 90%. So this is how you interpret the chi-square table. Till now, we haven't studied hypothesis testing. Now, when we will enter into hypothesis testing, then you will understand that how to use chi-square statistics and how to read the chi-square distribution table properly. Currently, I just build an intuition how to read chi-square table and what are the different components of chi-square table. So when we'll enter into hypothesis testing, then we'll understand exactly what is the usage of chi-square table. But in this session, we are able to cover the different components of chi-square table. We understood what is the interpretation of degree of freedom. So here the degree of freedom is not n minus 1. Here the degree of freedom is the standard normal variable, the number of standard normal variable we are playing with. This is the area in the left hand side of the point, and these are the point on the x-axis. With that, we'll pause here and we'll see you in the section of F distribution. Thank you. Have a nice day.